Good morning, all. There are 17 students who have joined here today. Thank you for joining. We will start our class on statically indeterminate beams. We have learned few techniques. One of them is integration. Well, in everything we are doing integration only. Integration of governing differential equation, right? Differential equation. Next is discontinuity method or Macaulay-Becker method, right? Apart from that, we learned two more methods which are easy, but they are specific to particular point. If you want to find deformation or slope at a particular point, these methods gives you quick and easy solutions. And these are, one of them is moment area method. And there are two theorems for moment area method, right? One to calculate slope, the other one to calculate deformation. Or they don't give, moment area method doesn't give deformation, it gives tangent deviation, okay? And the fourth method that we learned is Castigliano's method, right? Right, that is based on strain energy principle. Strain energy, right? These two methods are mostly suitable for when you want to find deflection at a particular location. And these two methods are suitable for when you want to find deflection for full beam, okay? Deflection curve for complete beam. And this is for deflection at a particular point. Okay, it's slope or deflection, either of. When I mean deflection, I mean both, right? All right. Today we are going to use them to find deformations or to solve statically indeterminate beams. Okay, so what are statical indeterminates? We have discussed about statically indeterminate structures a long time. Whenever we discussed about axial members, whenever we discussed about torsional members, we have discussed about statically indeterminate structures. In case of beams also, the main theory remains the same, that if your number of equation is lesser than your number of unknown reactions, then the structure is indeterminate. In that case, the degree of indeterminacy, a number of indeterminacy, is the number of unknown forces, unknown reactions minus number of degrees of freedom that you have gives you the number of indeterminacy. Okay. If your unknown reaction is more than number of equilibrium equations, then it's become your indeterminate structure. So for, let's say this one, we call it a propped cantilever beam. This is called propped cantilever beam. A prop cantilever beam is because this is a cantilever and there is a prop here, okay, to stop deformation or to have zero deformation at the free end. So that's called prop cantilever beam. And a prop cantilever beam has a load which is inclined load, okay. Now, since there is a load that is inclined, we will have horizontal reaction here. And since this is fixed, obviously there will be a moment, unknown moment, and there will be an unknown reaction force. Okay, with all those things, unknown reaction force, unknown horizontal force, and unknown moment on the point A, and the support B will have a vertical force, right? I'm not assuming that this is fixed, this is hinged, this is a roller support, okay? If this is a roller support, there is only RB that will be there. So RA, RB, MA, HA all includes to 4 unknown. Okay, 4 unknown forces, and number of equations you have is summation of vertical force equal to 0, 1, 2 is summation of moment equal to 0, and 3 summation of horizontal forces equal to 0. So 3 equations. So 4 minus 3, number of indeterminacy is 1. So we will need 1 extra equations to solve this problem. And that extra equation, as you all know, should come from the compatibility conditions. Okay, so we will learn how to find them. For example, in this case, it's going to be deflection at B is equal to 0. Right? That is one extra equation that we get, and we can use that equation to solve the unknown reaction forces. And once you know the unknown reaction forces, we can solve for his bending moment, we can solve for his shear forces, we can solve for everything that we need. Okay. The next problem is a fixed beam. Okay, this is called a fixed beam, and this fixed beam has 3 unknowns on this fixed side and another 3 unknowns on this fixed side, right? So both A and B will have 3 plus 3, 6 unknowns. But number of equations again remain same, it's 3. So therefore your number of unknown is 3. Number of indeterminacy is 3. Okay, so therefore we will need 3 extra equations to solve this problem. What would be this extra equation? Moment at this point B is 0. Slope at this point B is 0. Deflection at this point B is 0 vertical deflection, and horizontal deflection also at this point B is 0. Okay, clear? Now the third example is a continuous beam, which is a simply supported beam and it extended for another simple support, right? So it's called a continuous beam. So we have, if we have inclined loads again here, we'll have horizontal unknowns. So these two are roller supports. But with roller supports here, number of unknowns, we have 2 here, plus 1 here, plus 1 here, right? So it becomes 4 unknowns. And obviously we have only 3 equations. So that also becomes 1 degree of indeterminacy. Okay, here also we will need only one compatibility condition that can solve this problem. Okay, let's solve the first one. If you have any question, anyone of you have any question?
No, sir.
No, right, thanks. So next part is we solve one problem first. We have a propped cantilever in this case, where there is UDL acting, uniformly distributed load acting on the beam. Okay. Uniformly distributed load is shortly called as UDL. All right, so there is a UDL on the beam, and it's a propped cantilever. It's an indeterminate structure with an indeterminacy of 1, right? So number of reactions are, unknown reactions are RA, MA, and RB is equal to 3. Excluding horizontal reaction forces, we don't need horizontal reaction forces because the load here is vertical. Number of equations of equilibrium is 2. So the structure is indeterminate with degree 1. Okay. Right. Now we can use one compatibility equation. What is that? I already said that the easiest compatibility condition will be RB provides force such that delta B is equal to 0. Okay. So the force RB is such that delta B comes out to be 0. Okay. So that should be my compatibility condition. And we can use that. So now I will have summation of vertical forces equal to 0. So my equations that I have, summation of V equal to 0, summation of M equal to 0, and delta at B equal to 0. So I have 3 equations, 3 unknowns. I can solve it, right? Okay, but what I'll do is, instead of going straight forward way, I will use superposition principle to solve this problem. Let's see how we use superposition principle. So this beam, rightly what you have right now, this is my main beam, right? The original structure. I can divide it, since deformation and load relationship is linear, right? I can divide the structure. I can use superposition principle. So one part of the structure is a cantilevered beam with a UDL. The other part of the structure is a cantilever beam with a point load. What I'm doing is I have removed the support from here. Like in earlier cases, I have removed the support, and after removing the support, I have to give that reaction force, right? I cannot only remove the support, I have to fill up with a reaction force. So I'm giving a reaction force RB, which is not known to me currently. I don't know what is RB, but I'm giving a force. So I've replaced the load. Now the beam is now under 2 loads. One is UDL, the other one is RB. With these 2 loads, the beam's deformation should be 0 here at B point. Okay. So I can divide the load, subdivide the load into 2 parts. One is cantilever beam with a UDL, another one is cantilever beam with RB. Remember, the RB direction is upward here. Okay. So let's say the deformation due to UDL is delta B1 at B point, okay, at B point, and B2 at B point for the point load. Now, from my compatibility condition, what I have, total deflection at B is supposed to be delta B1 plus delta B2, and that should be equal to 0, right? That's my compatibility condition. And I have to, now what is the job? My job is to find what are delta B1 and what are delta B2. Now, we know we have solved this earlier. We have solved this also earlier. So we know how to find delta B1 and delta B2. So let's look at structure 1. This is a cantilever beam with a UDL, and its bending moment diagram is going to look like a second order parabola here, right? And it will be downward, right? Okay. So delta B1 using moment area method is A into x bar to be calculated from this point. So your area is, since the area of a parabola, it is 1/3, L is the length here, and the height is the base or height, whatever you want to say, WL square by 2EI. So this is your area of the area under the M by EI diagram, right? Bending moment by EI diagram, and that should be multiplied with the arm, right? Moment arm. So momentum should be calculated from B point, and it's going to be somewhere here. So 3/4 L. So this becomes your delta B1. You can use Castigliano's theorem also. You will get the same value. Okay. So this is deflection due to UDL at the free end. Now we have the second structure to solve. The second structure is a cantilever beam with a R load at the free end acting upward. So its bending moment diagram is going to be something like this. Remember that now this is positive bending moment. Earlier it was negative bending moment. Okay. All right. So because this is going to give us sagging deformation like this, right? So tensile at the top, bottom, and compression in the top, right? So it's a sagging moment. So M by EI diagram is going to be RBL by EI in the tip. So its area is again a triangular area. So you can calculate half into length into height, and then the center of the triangular area from the B point where you are calculating your deformation is going to be 2 by 3 L, and this is going to be your RB L cube by 3I is your deformation at the free end, right? So this is delta B2. So now I know delta B1 plus delta B should be equal to 0. Now one of them should be negative because one moment bending moment is negative. So this is my negative deformation, and this is a positive bending moment. So this is my positive deformation. So minus delta B1 plus delta B2, right? So this minus sign comes here, and once you solve it, you get RB equal to 3/8 WL. This is a nice formula to remember. RB is 3/8 WL. Now I have got it positive, right? No sign here. It's a positive sign here, right? Now positive sign meaning the direction I've considered for RB is correct. Therefore, RB is going to be upward only. If the negative sign would have come, then my direction is this I've considered. The actual direction will be downward in that case. But in this case, it's a positive. Therefore, it is acting upward RB. Now, once you put RB as upward, now you know the value of RB. It is easy to solve. Use your equilibrium equations to solve for RA. So RA is going to be WL minus 3/8 WL. So it's going to be 5/8 WL. And use your moment equation, anti-clockwise moment to be positive. You get your MA as WL square by 8. Okay. So these two solutions, now the beam is completely solved, and I can draw its bending shear force and bending moment diagram. The shear force diagram, as I know, can be you also know how to draw it. You can draw it using superposition principles also, right? Okay. So, but I have solved it here, and you can see how it has been drawn. So your bending moment diagram is going to look like this. Remember that with a UDL, it is supposed to be only like this, which has become some part is negative, some part is positive because of the prop cantilever. Similarly, SFD, which was supposed to be only triangle like this is still triangle, but there is a sign change in SFD at this location. Okay, so this location is going to be the point where you have maximum bending moment in the positive direction or negative direction. So this is how the superposition is done for the bending moment and shear force diagram. So for UDL, your shear force looks like this. For point load, your shear force will look like this, right? So you add them together. So this is what happens when you add them together. So this is your point load, right? And you start your triangle over this, making this as a base. It is on the opposite direction because one is positive, one is negative. That's why. So this part is not there. Only this part is your shear force triangle. Similarly, bending moment. The bending moment for this is triangle, and for this is this guy, right? So, but there is a sign change. This is negative, and this is positive. Okay. So there will be a change in direction. So let's say this is my positive, and over which I have to draw the negative triangle. So it will go like this. So your actual bending moment diagram is this. Okay. All right. So with that, I'll pause. Yeah. Okay. So this is the problem with again with one degree of indeterminacy, and as you can see, there is a support at the center of a beam, right? And therefore, there are three unknowns, but we have two equations. So this unknown, this is an indeterminate structure. Now, which support shall I remove and provide a reaction force? Let us first try C. If I remove C, this is a beam that will look like this, right? No, there is no. Okay, and then there will be here RC and there will be UDL. This is a simply supported beam with overhang, not a difficult beam to solve. It's easy beam to solve, but still it's a little bit more involved. Let's see any other choices are there or not. Let's look at A. If I remove A, what happens? So if I remove A, what will happen? It will happen the same thing, right? So I will have a force here, RA. There is this support. There is this support, right? Okay, there will be two forces here, RA and RB. So what I can do is I can remove, okay, RA is not there because it's 0. RAH will not be, the horizontal force will not be there because that will be equal to 0. Only the vertical forces. But still, it is same as the first try, right? First try. This is my trial 2. Trial 1. Same thing, right? So I'm not getting anything changed. So let's say my trial 3. I will keep both the end supports intact, and I'll remove the center one and put a board RB here. This is a simply supported beam with a UDL and a simply supported beam with a point load. Both of its solutions are easier to and should be known to us, right? Very easy to solve and known to us for most of the cases. So I think this is going to my right choice. Okay, so this is my right choice. So I will remove support B and put a reaction force there. A reaction force such that RB is of such value that delta B equal to 0. Okay, I'll write that if you need to. RB is of such value that delta B goes to 0, right? So this is my compatibility condition. Delta B is equal to 0. Now delta B should be due to two loads. One is UDL acting from up to down, and one is RB acting from down to up, right? Point load. So I'll divide the beam into two parts. Again, first part is only the UDL. The second part is only the RB. Now this time I'm using strain energy principle. Please do it yourself. Your delta B1 is coming out going to be 5Q by. So strain energy principle, we know the formula for this, I think. So I've just put 2L instead of L here, and we get this formula. So that is the delta B1, and it is downward, right? So I've kept it negative. And this is upward. We also know for point load what will be the deformation. It is PL by 48 EI. Now instead of L, it will be 2L because length becomes L and L. So this length is 2L, right? So it is RB 2L by 48 EI. That comes out to be this. Now both of this will add up to give me deformation at B0. So they should be equal. So when you put them, you get your RB as 5 by 4 QL. So once you know RB, I have only two unknowns and I can use two equations, summation FB equal to 0, summation AM equal to 0 to solve the complete beam. And that you can do yourself, right? Rest of the thing, do it yourself. Any question on this? So try to solve as many problems as you can. Solve this problem also if you can. Okay, so instead of a support, I have a spring here. Okay, so this is called support settlement problems. For example, this comes from a real structure. Let's say you have a beam-like structure, okay, and you had a support here. So you know that the support, the beam, the soil here is not of good condition, so it can fall in. So it can go like this. Okay, and this is your deformation. This is called support settlement. So based on the soil condition, you can write that since my support is not very strong, it will have some cushioning effect, soft soil. So there is a K stiffness of the soil. Okay, so that kind of problem is this one. Now solve this problem. Okay, you have to solve it, right? You do it now or do it later, but you have to solve it. We have to get into stability of columns, and we will first learn stability, the defined stability, and then we will get into columns in the next part, next video. While talking about stability, I will say that we are not talking about stability in purely mathematical sense. There are theories available which teaches you about stability of dynamical systems. You have learned stability a little bit for trusses. When a truss becomes stable, when a truss is unstable, right? So if I remember, you have learned that R plus, I forgot that 3m equal to R plus J or something like that. Reaction plus joints should be equal to 3 into number of members or something like that formula was there, right? So in stability is a big part of structural mechanics, right? So we already said to you that there are three parts in structural mechanics. Okay, one is strength. Strength, we learned that strength is from material point of view it comes, and that is either your ultimate strength or your real strength or your design strength, whatever you want, should be your definition of structural strength. So you should not go beyond the design strength by factor of safety, right? For your design of your structures. So that's from strength of point of view. There is another thing I said, that stiffness point of view, right? The stiffness of a structure is measured because of its geometric deformations. It comes because of the boundary conditions of the structures. For axial structures, it is AE by L, AE by L. For torsional, it is GJ by L, and for bending, it is EI by L. Depends on boundary condition. Again, as I said, for bending, boundary conditions are different, and therefore your stiffness will be different, right? For example, for a point load beam with a point load, we learned that deflection is equal to PL cube by 3EI, right? That's what we learned. What was the deflection? Where is the point load? Yeah, PL cube by 3EI. See here, RB L cube by 3EI. So PL cube by 3EI, and therefore its stiffness K is equal to, stiffness is what? 3EI by L cube. Okay. All right. So it is a load required for per unit deformation. Stiffness is given as the load required for per unit deformation. So if you put delta is equal to 1 and you want to find P, that will be your 3EI by L cube. Okay. So that's your stiffness here. And the next is, our next important part of the structure is stability, whether a structure is stable or not. Okay, a structure the load may be within the strength of the structure, the deformation should be within the given limits, so stiffness is in a reasonable amount, but even the structure can be unstable. That means you give some kind of different load, the structure may fail. Just now we solved one problem, right? Where we saw that you have this structure and we removed the support at A, right? And we said there will be point load. This structure is an unstable structure. You give a load like this, it is unstable. It is stable as long as your load is vertical. But as you move the load a little bit, the structure is unstable. The structure will, because of the horizontal load, the structure will start moving. It will have rigid deformations, right? And that is not allowed. The structure is not allowed to move. So I don't know, it might be fun, right? Today I'm here with my building and tomorrow I may be in Mumbai with my building, right? So day after tomorrow I may be in a jungle. So I don't know that's good thing or not. But structures cannot be designed that way. For example, you know that 4-member truss is an unstable structure. Just a slight point load, it will just fall like this, which is not allowed, right? Large deformations are not allowed. So what you do, you put a member in between, a bar member in between, so that that bar member can take the horizontal load. But how do you check stability? Okay, how is the stability checked? How do you check stability? Well, what we do is, let's say you want to get up a ladder and go onto your roof or in the next building, or your girlfriend is in the first floor, you go and want to give a flower, so you put up a ladder and get up, right? And in the veranda you want to give a flower. Before, you might be very excited, I know, but before you get onto the ladder, the wise idea will be to move the ladder a little bit and check whether the ladder is stable or not, right? So that your girlfriend's father do not come and just push it and you fall down. Should not happen, right? Therefore, you have to check it, whether it's stable or not. So what you do, you just move a little bit the ladder, you perturb the ladder from its initial position, whatever position it is, its current state, and see whether the ladder falls down or not. If the ladder falls down, then it is not stable. But if the ladder goes back to its stable configuration, in a sense, its state of state, wherever it was, then you know that if you go onto the ladder will not fall. The frictions are good enough, right? This is how you check. So when a system is unstable, you want to make sure that it's stable. You just perturb it a little bit and see. You have done it many times in your life. And mathematically, you have probably not done it. You will do it mathematically once you take stability of structures, or you take stability of dynamical systems as your part of course. Here, we just give you a hint on stability, right? There is another example. Let's say I have a pendulum, ulta pendulum. Ulta pendulum is stable or unstable? We know that a pendulum of this sort is stable, right? Why it is stable? Because if you perturb it a little bit, and leave, it will come back to the same position. Right? So that means that position of the pendulum, this position of the pendulum is a stable position. Now I can keep the pendulum also like this. As long as I will keep it and without disturbing it, it will stay there, right? It will not move from that point if I don't disturb it at all, neither by wind nor by anything. Not even a mosquito comes and sits on it. Nothing. It will stay in its vertical position as it is lifelong. But if you do a slight perturbation, let's say a mosquito comes and just perturbs it a little bit, tongue, what will happen? It will not stay in this position. It will have a large movement from that position and probably come and stable here. So there will be a large deformation here, large displacement here, right? Therefore, this position of the pendulum is not stable. But you can make it stable. How do you make it stable? There are various ways of making it stable. One of the way is you put a spring here, right? Then now you perturb it. It goes this position. The spring will pull it back, right? So it will come back here. So spring will provide the restoring force. It's called a restoring member. Spring will provide restoring force and it will come back to its vertical position. You can also give something like this. you give a torsional spring at the bottom along with the supports. Now what happens? If you move it, right, what will happen? You see, because of the torsional spring here, there will be a moment that will act here, right? And the moment will again bring it back. The restoring force is the moment here. Okay. All right. So this is how you check stability and how you can stabilize a unstable system. This is the part of our course. Normally, a stable system is assumed to be a ball in a bowl, right? So if you move the ball will come back to its again the same position. So this is its state of equilibrium. Once you have the state of equilibrium, you perturb it from the state of equilibrium, it will come back to its equilibrium. That is called stable. But if you perturb it from, this is an unstable position. So if you have ulta bowl, inverted bowl, and if you perturb the ball from that bowl, the ball will fall down, right? It will not come back to its initial stable position. And therefore, this is called unstable. There is something called neutral stable, which is like this, where you perturb the ball will go to a new stable position. It will not come back to its initial part, but it will go to a new stable position. These are called neutral stable systems. Okay. What we have in a syllabus is vertical rods. Okay. And you have to find the value to make sure the system is stable. Okay. Or after what value of P load will the system become unstable? This is your part of the course. I've discussed this too already. Let me solve one problem. All right. So this is a structure. Okay, it is linked at point B, and there is a spring force at point B, or torsional spring, or rotational spring. The upper part of the bar CB is rigid. Below part of the bar AB is also rigid. So when I say rigid, that means they make an angle theta like this, and that angle theta is constant all through, right? So it is not bending like a beam. Okay? It's like a rigid rod. All right. Now, if you give a load P here, please note the boundary conditions. Here it is a roller. Here it is a hinge support. That means this guy is free to rotate. This joint is free to rotate, and it can have like this. Okay. This part is a roller on the side. Therefore, it is free to move in this direction, and also it is free to rotate. Right. So both the boundary conditions are open. So if you put a point load on the top, what will happen? This will push downward because this roller support will not support that point load acting along that direction. So it will come down, right? Once it comes down, this will make there is a hinge here. So it will bend, this will bend, and this will take a moment. So the condition will be something like this. Let's say it makes an angle theta. Now, how do I find the value of P for which the structure will not remain stable? The structure will be unstable. How do you find that? Okay, what is the value of moment that is being supported by this spring? It will be spring constant Br into the rotation angle theta. So Br into theta in one side and Br into theta on the other side. So it becomes 2Br into theta as your moment, restoring moment. So this is your restoring force. Okay. And what will be your moment by the load that is coming here? So if you take a free body diagram, you get a P force here, you get a P force here, and this is the distance that that is your moment arm. So it becomes P into theta L by 2. So this length is L by 2. So P into theta L by 2 is your moment given by the force P. So they should balance each other, and therefore you get the critical P as 4bi by L. Okay. Now what happens if you draw the structure? When your force is 0, P is 0, the structure has no deformation, right? This is my theta angle and this is my force angle. I am drawing it in a theta P frame, right? Theta P axis. So when your force is 0, theta is 0. When your force goes a little bit up, theta will be 0 because the spring will take care of the moment, right? That is generated by P. It goes a little bit up, there is no theta. It goes a little bit up, there is no theta. But it goes to a point where is the critical value here that comes from this value, after which the structure will not have a zero deformation, right? Zero slope or zero rotation. It will have suddenly a finite rotation. It can have this side or it can have that side, because it depends whether it can go this side or this side. That depends on the, if it is an ideal structure, homogeneous structure, then it can take any way, any direction. It depends on if there is a little bit weakness on any side, it will take that side. Right? So it can go this way or this way. So this is the point. This is the critical point after which it will have large rotations. Okay, this point is called bifurcation point. It's called a bifurcation point because the beam has the structure has two direction, right? Bifurcation, bi is two directions to move. It can either go this way, it can go like this, or it can go like this. Okay, so that's the bifurcation point for this structure. With that, I'll stop. There are a few more problems that you can go in the Hibbeler and check, where they are solved it with springs, with similar problems with springs, with a little bit more single. This is a double member. There is a single member problem also, which you can solve, and they also give a mathematical formula to check stability. Okay, please check the book Hibbeler, and we will discuss about this in the next class also. All right. Tomorrow we will start with columns. But this is an interesting subject. Stability is an interesting subject, especially for those who wants to go and work in the dynamics area. It is very important for static point of view. I'm telling it's not important, but from dynamics point of view, it has rich things to show you. It has a rich flavor. There are a lot of unknown problems because dynamics and stability is just 150 years old. It's not a lot old.